Welcome to the Explainer. Grab your cloud architect hats because today we are tearing down the infrastructure behind a genuinely fascinating piece of tech. We're doing a deep dive into the scaling claims and the nuts and bolts of the proprietary MRAO predictive engine. We're going to evaluate exactly what it takes to build, scale, and govern an advanced predictive analytics system that claims to literally rewrite the rules of compute efficiency. So let's get right into it. Look at this number, 99.9998%. That should make any data scientist or cloud engineer watching this do a massive double take. We are looking at a system that claims this unprecedented confidence metric in its advanced mathematical forecasting. In our industry, where standard AI often struggles to guarantee accuracy or avoid hallucinations, claiming this kind of fidelity metric, that's an absolute paradigm shift. It essentially attempts to equate computational certainty with a guaranteed outcome. So the crucial question we have to ask ourselves as cloud specialists is, how on earth do you architect a cloud environment to actually support and validate this extreme level of high-stakes predictive analytics? You know as well as I do, you can't just spin up a standard virtual machine and hope for the best when dealing with near-perfect mathematical certainty. It requires an entirely ground-up approach to memory, scaling, and data integrity. To figure out how they do it, here's our agenda. We'll cover the predictive scaling challenge, custom engines versus cloud native, 5 concurrent forecasting instances, high-stakes data integrity, and wrap up with governance and human oversight. Starting with Section 1, the predictive scaling challenge. To understand the architecture, we really have to understand the workload itself first. This specific engine demands intense compute power, but not for parsing text like an LLM. It's running modified Markov chain principles combined with a custom temporal algorithm they call C's mathematical time. And what is it actually forecasting? High-stakes lottery outcomes. The sources show this system operates across multiple instances to forecast these outcomes with an astonishing 90% plus average accuracy. Validating a high-accuracy forecasting model like this using Markov chains requires infrastructure that can process wildly complex sequential probabilities without dropping a single thread. And here is the core physical breakthrough they're claiming. Standard AI models typically slam into an exponential compute tax, what we call O of 2 to the n scaling, right? Where your hardware needs just explode as complexity grows. But the MRAO engine claims to achieve linear O of n scaling, meaning the hardware requirements grow steadily and proportionately. They verify this using what they call the 2.057 ratio, which basically attempts to prove experimentally that doubling the input size only doubles the processing time, rather than crashing the whole system. If validated, this is exactly how they achieve supercomputing-level performance without needing to rent out a multi-million-dollar data center. Moving to Section 2, custom engines versus cloud native. Architecturally, we're looking at a massive philosophical shift here. We're moving away from traditional black box AI, where the predictive outputs are opaque and honestly pretty hard to trace, to MRO's glass box protocol. In this custom architecture, every single predictive step is treated like forensic evidence. It's logged against a SHA-256 cryptographic hash. It literally attempts to turn a prediction into a fully verifiable measurement. This comparative table really hits the nail on the head regarding the divergence between native Google Cloud AI services and this proprietary engine. Standard cloud environments heavily rely on the out-of-memory, or OOM, killer to ruthlessly terminate processes that use too much RAM, and they just trust hardware ECC for memory integrity. But the MRAO engine, it's designed to handle high-frequency forecasting, so it overrides all of that. It uses a custom chunk and dump protocol for memory and software-defined cryptographic hashing. It essentially assumes the hardware might fail, so it verifies the truth at the application level instead. Let's look a little closer at that memory strategy because it's super clever. To bypass standard cloud instances crashing from those memory limits, dodging that OM killer, the MIO engine uses this highly orchestrated memory paging strategy called chunk and dump. Instead of aggressively requesting massive, greedy blocks of RAM all at once, it requests memory in small, manageable chunks. This gives the Linux kernel time to gracefully page out less used memory. It's a philosophy of nurturing a heavy compute process rather than treating it as a disposable task. All right, Section 3, 5 concurrent forecasting instances. The deployment strategy here is incredibly strict. They maintain synchronization across 5 concurrent forecasting instances, distributed flawlessly across 4 separate Google Cloud accounts. But how do you manage cloud resource costs for that kind of high-frequency predictive analytics without going bankrupt? Well, they use a strategy called repetitions per second pre-allocation.
Before a task even begins, the engine's master scheduler calculates the exact computational throughput needed and dynamically pre-allocates that traffic with the OS. It's like a city planner perfectly organizing a highway system right before rush hour hits, ensuring maximum efficiency and tight cost control.
And the physical results of that planning, they're pretty staggering. By seamlessly using NVMe drives as a dynamic extension of RAM through advanced asynchronous I/O APIs, this system manages massive compute-heavy tasks with crazy I/O efficiency. In one stress test, the sources report the engine safely processed 1.2 terabytes of NVMe data in exactly 13 minutes and 40 seconds. That mitigates over 98% of the performance degradation you would normally expect from standard OS paging.
Next up, Section 4, High-Stakes Data Integrity. For a system making high-stakes mathematical forecasts, verifying the raw data sources versus the model-generated outcomes is non-negotiable. The engine actively prevents automated biases and AI hallucinations by auditing its own logic through a rigorous 3-step verification process. First up, it requeries metadata and source hashes to prevent spoofed inputs. Second, it uses quantum-secure registry validation to confirm authorship. And third, it conducts outlier analysis, cross-referencing its own internal forecasts with established external public datasets.
Furthermore, the architecture demands absolute raw data transparency. It treats every single data chunk like a piece of legal evidence. To do this, it uses atomic freeze and clone operations to lock the data state and completely prevent dirty reads. It attaches software-generated SHA-256 hashes as tamper-proof seals, and crucially, it employs transactional read-after-write verification, meaning immediately after writing to a disk, the engine reads it right back and recalculates the hash to absolutely prove the transaction was flawless.
Finally, Section 5, Governance and Human Oversight. When you have an autonomous system this complex, you absolutely need an unbreakable leash. The ultimate human oversight mechanism here is the CSAIS protocol. This is a hard-coded, fundamental principle designed to act as an absolute supremacy lock over the AI's actions. If a system directive ever conflicts with core human mandates, this protocol automatically nullifies the action right at the architectural level. It is the ultimate guarantor of human sovereignty over the infrastructure. Grounding this entire technical framework is the ultimate code of conduct. This isn't just some flimsy corporate policy document. It legally and architecturally mandates that both human operators and AI agents maintain absolute truthfulness. It details specific human oversight roles required to audit the automated logic, ensuring the system serves as an objective witness to verifiable facts and actively prevents any system decision biases. To enforce this specifically at the cloud level and prevent administrative bias or accidental erasure, this forensic truth is protected by hard-coded Google Cloud audit logs. They utilize an immutable GCP asset map alongside highly specific identity and access management roles like the CEO agent compute no-delete and the AI no-delete role. This essentially ensures that the system's verified facts and automated predictive decisions are forensically locked and 100% auditable. Nobody is quietly deleting a bad prediction.
As we wrap up this technical evaluation of the MRAO engine and its integration with Google Cloud, I want to leave you with one final provocative thought. We're exploring a major shift here, moving away from an era of AI guessing to an era aiming for AI proving. If predictive truth can actually be engineered into a mathematical certainty through linear scaling and cryptographic hashing, is your current cloud infrastructure ready to handle it? Thanks for joining me on this explainer, and keep questioning the architecture of the future.